welcome to lecture number 8 of chapter 4 series. In this video, we are going to learn dependence of rate of reaction on temperature. Means how rate of reaction changes with temperature. That we are going to learn. The first point is written here that in most of chemical reaction, rate increases with temperature. Means with rise in temperature, the rate will increase. The mathematical relation between rate of reaction and temperature is like this. K is equal to A into e raised to minus EA by RT. This relation, this equation was given by scientist Arrhenius here, where this A is Arrhenius factor or frequency factor or free exponential factor, R that is gas constant, EA that is activation energy, T is temperature here. Now, what is activation energy? To understand that, take an example here. Suppose we have a reaction H2 plus I2 gives 2HI. All the components are in gaseous form. So, you can see here the gaseous form. So, in order to react with each other, H2 and I2, these both molecules, they will have to collide with each other. And this collision results into intermediate. This intermediate is not stable, so immediately it converts into HI molecule. Here you can see HI is our product. Now, if we draw a graph of potential energy versus reaction coordination, potential energy versus reaction coordinate, it will give us a curvature graph, and you can see here first point is our reactant H2 plus I2, then potential energy increases, then at the highest peak point it is our intermediate activated complex, then the potential energy lowers down and becomes very low and gives us product. Last point is our product HI. Here the energy gap between activated complex and reactant, that energy gap is called activation energy. And here you can see the energy of product is lower than energy of reactant. So gap between them, the energy gap between them, it is called enthalpy of reaction, delta H. Now we saw that H2 and I2 molecules, they will have to collide with each other in order to react with each other. So each molecule, suppose we have 5 grams of H2 and 5 grams of I2, in that number of molecule will be there. Now each molecule have different kinetic energy, but the molecular kinetic energy अलग-अलग है. So they will collide in different manner. So we can't derive the exact kinetic energy of each and every molecule here. So to overcome that, Ludwig Boltzmann and James Clerk Maxwell suggested a way. According to them, in order to predict the behavior of large number of molecules, they plot a graph of fraction of molecule Ne by Nt versus given kinetic energy. Now what is Ne? So Ne is molecule with number of molecule with kinetic energy E, and Nt is total number of molecule. Now you can see the graph to understand it better. Here fraction of molecule versus kinetic energy graph is shown. Fraction of molecule means Ne by Nt. Here you can see the highest peak that shows that maximum molecule will have this much of kinetic energy. Maximum molecules, not all molecules, but maximum molecule will have this much of kinetic energy. So this is our standard line, and on the right hand side, this side, molecules will have higher kinetic energy, you can see here, and this side molecules will have lower kinetic energy. Now in order to calculate the in order to understand the behavior of collision here, take this standard value as constant. Take this value, this kinetic energy for all the molecules. Now suppose in the reaction I am increasing the temperature. Now by increasing the temperature, I can say that I am giving some energy to the molecules. So this energy they will use in, and they will have the energy in form of kinetic energy. So molecules kinetic energy will increase here. So due to that, the graph will be changed here. You can see here two curves are shown, T and T plus 10, means temperature small t and temperature with 10 degree extra heat. So you can see the graph here. First observation of graph, you can see the curve is slightly shrinked here. So here the third observation I have written, shrink in curve is observed. Now you can see the line in previous slide, the line was in middle of curve, somewhat middle of curve, but here the line is shifted towards right hand side. So with increase in temperature, molecule will gain some energy. So the most probable kinetic energy, that line shift towards line right hand side, because the molecule are gaining energy. So maximum number of molecule will have some higher energy now. So this line shift to higher kinetic energy side, means right hand side. And the third observation that we can observe here on the right hand side, that this area, you can see the gray area, that is extra one, that shows that molecules are gaining energy and they are having higher energy compared to first temperature T. Now we saw the Arrhenius equation, K is equal to A into e raised to minus Ea by RT. Now from that we are going to derive a formula here. First take natural logarithm on both sides. Ln K is equal to ln into A, ln A into ln A into e raised to minus Ea by RT. Now this is multiplication, A into e raised to minus A by RT. So in logarithms, if two values are in multiplication, we can write two different logarithms with addition sign between them. So I have just expanded that equation here, ln A plus ln e raised to minus Ea by RT. Now this one is in minus Ea by RT is in power of e, so it will come in multiplication, and ln e, that is equal to 1. So I will get ln A plus minus Ea by RT into 1. So I have not written 1 here. Now this is our equation number 1. Now if we draw a graph of ln k versus 1 by t, from that graph we can see that the slope of that line, it will give a straight line, and the slope of that line will be minus Ea by RT, and the intercept will be intercept will be ln A. Now suppose two different temperatures are given to you, T1 and T2. At T1 temperature, the rate constant K is equal to K1, and at T2 temperature, the rate constant K is equal to K2. Now for that both conditions, write down the equation number 1. So I have written ln K1 is equal to ln A plus minus Ea by R T1. ln K2 is equal to ln A plus minus Ea divided by R T2. Now subtract these both equations. So I will get ln K2 minus ln K1 is equal to minus Ea by R T2 minus bracket minus Ea divided by R T1. Now these both are in subtraction, so I can write these two values K2 and K1 in division here. So K2 by K1. Now convert ln into log. So we have to multiply it by 2.303. So I have written on another side of is equal to in division here. Now minus Ea by R is common in this both. Now it is I have taken it in common, Ea by R, and you can see 1 by T2 and 1 by T1. So I have changed the place here. Minus minus will be positive, so 1 by T1 is positive here, minus 1 by T2. So this is our required equation. From this equation we can derive rate constant as well as temperature and activation energy also. Okay, thank you.